Welcome to the deep dive. Today, we're taking a bit of a shortcut into, well, the pretty complex world of aromatic compounds. These are molecules that pop up absolutely everywhere, in nature and industry. You sent us a really great starting point, a chapter from Organic Chemistry and I for Dummies, seconded. So our goal today is really to pull out the key stuff, cut through the jargon, and basically give you what you need to spot these rings and, understand why they act the way they do.
That's right. We'll be digging into the basic ideas of aromaticity. We'll look at why molecular orbital theory is so important for their stability, tackle some common mistakes people make, and yeah, give some practical tips for figuring out if something's aromatic or, say, predicting how it might react.
Okay, let's start with the name itself, aromatic. It sounds like it should smell nice.
Yeah.
Right? And yeah, it's true. Many of the first ones they found, like in vanilla or wintergreen, they did have strong smells.
But the smell, it turns out, has basically nothing to do with what makes them chemically special. Lots of them don't smell at all, or some actually smell pretty bad. It's not about the nose.
Right. And the story of benzene, the sort of parent compound here, is pretty cool, isn't it?
Oh yeah, it's fascinating. For ages, chemists just couldn't figure out its structure. The famous story is about Auguste Kekule, who supposedly dreamt of a snake eating its own tail. And that, sparked the idea of a ring structure.
A bit of a legend, maybe, but the ring idea was dead on.
Exactly. His intuition about it being cyclic was absolutely correct, even if the dream part is a bit dramatic.
And that ring structure, that cyclic nature, is totally critical to how they behave. Unlike a normal alkene, which reacts pretty easily, these aromatic compounds are incredibly stable, almost unreactive sometimes.
Yeah, the source puts it really well, trying to react them with mild stuff. It's like shooting pop guns at a well-defended castle.
Yeah, you need the heavy artillery, the howitzer reagents, to actually get them to do anything.
And that lack of reactivity, even though they look like they have double bonds, is really their defining feature. It sets them apart. They're treated as a whole separate functional group because their chemistry is just so different from typical alkenes.
So, okay, how do we actually draw benzene then? Because you usually see it with those alternating single and double bonds, but you said that's not quite right.
Yeah, it's a simplification. The real picture is more like a hybrid, a blend of two resonance structures. The key thing is all the carbon bonds in benzene are exactly the same length. They're somewhere between a single and a double bond, 1.5 bonds, you could say.
Okay.
Some people draw a circle inside the hexagon to show those spread out pi-electrons, which is maybe more accurate visually. But the source, and often chemists' drawing mechanisms, tend to stick with the alternating double bonds, just keeping in mind it is a hybrid.
Right. It's a shorthand. And benzene isn't the only one, right? There's a whole family.
Oh, absolutely.
Yeah.
A huge variety. You get fused rings like benzopyrene found in things like coal tar. Unfortunately, some of those larger fused ones can be, well, pretty nasty. Benzopyrene was linked to cancer in chimney sweeps way back when. And aromatics aren't just carbon rings either. They come in different sizes and often have other atoms mixed in heteroatoms like oxygen, nitrogen, sulfur. Think of molecules like furan or pyridine.
And they're everywhere in biology, too.
Totally ubiquitous. All our DNA bases, adenine, guanine, cytosine, thymine, they all have aromatic rings. That stability is crucial for holding our genetic code together reliably.
Okay, so they're rings. They look like they have double bonds, but they're super stable. What's the actual secret? What makes something aromatic? You'd think maybe just any ring with alternating double bonds would do it.
That's exactly what chemists thought at first, but nope, it turned out to be wrong. Take cyclobutadiene. Four-membered ring, alternating double bonds, should be aromatic by that logic.
Yeah, it sounds like it.
But it's incredibly unstable. It reacts with itself almost instantly. It's the opposite of stable.
Whoa, okay, so what's the difference then?
Well, benzene is way more stable than if you just had those double bonds in a straight chain. But cyclobutadiene is actually less stable than its straight chain version. This led to this idea of aromatic compounds being stabilized and anti-aromatic compounds being destabilized.
Right. And this is where Hückel comes in.
Exactly. Erich Hückel, a German chemist, figured out the pattern. He noticed that flat cyclic rings with a very specific number of pi-electrons were aromatic and stable. And that number followed a rule, 4n plus 2 pi-electrons, where n is just a whole number, 0, 1, 2, 3, and so on.
4n plus 2, okay.
But if a flat cyclic ring had 4n pi-electrons, it was actually destabilized. It was anti-aromatic.
So let's check. Benzene has 3 double bonds, 2 pi-electrons each. That's 6.
Right, and 6 fits 4n plus 2 if n equals 1. So aromatic.
And cyclobutadiene, 2 double bonds, 4 pi-electrons.
That fits 4n, again with n equals 1. So anti-aromatic, unstable.
Okay, that makes sense. But why that specific number? Resonance helps explain some stability, but why 4n plus 2?
Well, for the deeper why, you really need to look at molecular orbital theory.
Molecular orbital theory. Okay, this sounds like it could get complicated.
It can seem that way, but the basic idea is actually pretty neat. See, simpler theories often picture electrons as being stuck in a bond just between two atoms, like a little fixed path. Molecular orbital theory lets the electrons, specifically the pi-electrons here, spread out over the entire molecule. Think of it like the electrons moving from a tiny two-atom cubicle into a big, open-plan office that covers the whole ring.
A spacious suite for electrons. I like that.
Exactly. This spreading out, this delocalization across the whole molecule into what we call molecular orbitals, or MOs, that's the key. We often use the Greek letter psi for them.
So how do we visualize these O's, this spacious suite?
We use molecular orbital diagrams. They basically map out the available energy levels for the electrons in the whole molecule and show where the electrons actually sit.
Okay.
And for rings, there's a really cool visual trick to build these diagrams called a frost circle.
A frost circle.
Yeah, you draw a circle. Then you draw your ring, like the hexagon for benzene, inside the circle. And here's the crucial bit. You have to orient the ring so that one corner, one point, is pointing straight down.
Point down. Got it. Why down?
Because where each corner of the ring touches the circle, that represents the energy level of one of the pi molecular orbitals. Putting a point down guarantees you get the lowest energy bonding orbital at the very bottom.
Okay. That's a neat trick. Easy to forget, I bet.
Very common mistake. So for benzene, you've got 6 carbons. Each brings 1 p orbital, so you form 6 pi molecular orbitals. You draw the hexagon point down in the circle. You'll see 1 point at the very bottom. That's the lowest energy MO. Then you'll see 2 points at the next level up at the same height. Those are 2 MOs with the same energy. We call them degenerate. Then 2 more degenerate MOs higher up, and 1 single MO at the very top.
So 6 levels, reflecting the 6 orbitals that went in.
Exactly. Now, benzene has 6 pi electrons. We fill these MOs starting from the lowest energy. 2 electrons go in the bottom MO, then 2 go into each of the next degenerate pair. So that's 6 electrons total. All the lower energy bonding orbitals are completely filled. And the higher energy antibonding orbitals at the top are totally empty.
It's like a perfectly filled ground floor and first floor of an apartment building. Very stable arrangement.
Precisely. That completely filled set of low energy bonding orbitals is the electronic reason for benzene's exceptional stability.
So what do these orbitals actually look like?
Well, each MO is a combination of those atomic p orbitals. Remember, p orbitals have 2 lobes, with a node, a place of 0 electron density, in the middle. For orbitals to combine in a stabilizing bonding way, the lobes that overlap need to have the same phase, same sign. If they overlap with opposite signs, it creates an anti-bonding interaction, which is destabilizing, and you get an extra node between the atoms. Generally, the more nodes an orbital has, the higher its energy. The lowest MO in benzene has 0 nodes across the ring, the next level has 1 node, and so on up.
Okay, that makes sense. More nodes, higher energy. Now, let's do the same for cyclobutadiene, the unstable one.
Right, frost circle again, draw a square inside, point down. 4 carbons, 4 p orbitals, so 4 pi MOs, get 1 MO at the bottom, 2 degenerate MOs in the middle, right on the horizontal midline of the circle, and 1 MO at the top.
Okay. And it has 4 pi electrons.
Exactly. So 2 electrons go into the lowest bonding MO. That's filled. Now you have 2 electrons left and 2 degenerate MOs at the next level. Hund's rule says electrons prefer to occupy separate orbitals with the same spin before pairing up.
So 1 electron goes into each of those middle orbitals.
Yes. You end up with 2 unpaired electrons in 2 different orbitals of the same energy. This makes cyclobutadiene a diradical, and diradicals are generally super reactive and unstable.
Wow. So the MO picture clearly shows why it's unstable. It doesn't get that nice filled shell stability.
Exactly. Aromatic systems have all bonding MOs filled, usually paired electrons. Anti-aromatic systems end up with unpaired electrons or electrons in non-bonding or antibonding orbitals according to the frost circle. It explains the 4n plus 2 versus 4n difference perfectly.
That's a really powerful explanation. Okay, so now we know why. Let's get practical. How do we actually look at a molecule and decide? Aromatic, anti-aromatic, or neither?
Right. This is a core skill. There are basically 4 checklist items. If a molecule meets all 4, it's aromatic.
Okay, what are they? Lay them out for us.
Number 1, it has to be a ring. No rings, no aromaticity. Simple as that.
Makes sense. Cyclic, what's 2?
2, the ring has to be flat, planar. All the atoms in the ring need to lie roughly in the same plane.
Flat. Okay, why flat?
So the p orbitals can overlap effectively all the way around the ring. If it's puckered, the overlap is broken.
Gotcha. Condition 3.
3. Every single atom in the ring must have an available p orbital that's perpendicular to the ring, ready to participate in that continuous pi system.
So no sp3 carbons in the ring itself, because they wouldn't have a p orbital pointing the right way.
Precisely. And sp3 carbon breaks the chain of overlapping p orbitals.
Okay. Ring, flat, continuous p orbitals. What's the last one?
The clincher. It must have the Hückel number of pi-electrons, furan plus 2.
Right, the magic number. So meet all four, you're aromatic.
Yep. Now, if it meets the first 3 ring, flat, continuous p orbitals, but it has furan pi-electrons instead, then it's anti-aromatic.
And if it fails any of the first 3 conditions, like if it's not flat or has an sp3 carbon?
Then it's just non-aromatic. It doesn't get the special stability or instability. It behaves more like a regular alkene.
Okay, that clarifies the categories. Let's talk pitfalls. That planarity one seems like it could be tricky. Can things choose not to be flat?
Oh, absolutely. It's a great point. Look at cyclobutadiene. 8-membered ring, alternating double bonds. That's 8 pi-electrons.
8 is 4n with n2, so if it were flat, it'd be anti-aromatic.
Exactly. And anti-aromatic is bad news, very unstable. So rather than be flat and unstable, it bends. It adopts this sort of tub shape.
Ah, so it sacrifices the perfect p-orbital overlap to avoid being anti-aromatic.
Precisely. By puckering, it breaks the continuous overlap, fails condition 2, planarity, and becomes non-aromatic, which is much more stable than being anti-aromatic.
Clever molecule.
Yeah.
Any others like that?
Cyclodecapentane is another example. 10 pi-electrons should be aromatic, 4n plus 2 with n2, but the inside hydrogens bump into each other, forcing the ring to pucker, so it becomes non-aromatic too.
Okay, so planarity isn't always obvious. What about condition 3, the continuous p orbitals?
Yeah, the classic example is cycloheptatrine. 7-membered ring, 3 double bonds.
It leaves 1 carbon.
That's sp3 hybridized. It has 2 hydrogens on it. That sp3 carbon breaks the continuous loop of p orbitals, so non-aromatic.
But what if you, remove a hydrogen and leave a positive charge there?
Ah, good question. If you form the cycloheptatriene cation, that carbon with the positive charge becomes sp2 hybridized. It now has an empty p orbital that can join the party.
So now you have a continuous ring of 7 p orbitals.
Yes. And how many pi-electrons? Still the original 6 from the double bonds.
6 pi-electrons, 4n plus 2, ring, flat, continuous p orbitals. It's aromatic.
Bingo. The orbitation is aromatic and surprisingly stable. The neutral molecule isn't.
Okay, the trickiest bit for me is usually counting the pi electrons, especially when you have heteroatoms like nitrogen or oxygen in the ring. How do you know if their lone pairs count?
That is definitely a common stumbling block. The rigorous way is always to consider the hybridization needed for conjugation. Take furan, the 5-membered ring with oxygen. Oxygen normally has 2 lone pairs. For the ring to be aromatic, it needs 6 pi electrons, 4 from the 2 double bonds. The oxygen can rehybridize to sp2. One of its lone pairs stays in an sp2 orbital, pointing away from the ring system. The other lone pair goes into a p orbital, aligning with the carbon p orbitals. That adds 2 electrons to the pi system.
So 4 from the carbons plus 2 from the oxygen equals 6 pi electrons. Aromatic.
Exactly. But only 1 lone pair could participate.
Is there a shortcut, like a rule of thumb?
Yes, there's a pretty reliable shortcut. Look at the heteroatom in the ring. If it's already forming a double bond within the ring, like the N in pyridine or one of the N's in imidazole, its p orbital is busy with that double bond. Its lone pairs are not part of the pi system and don't count towards the 4n plus 2 rule.
Okay, double bonded heteroatom lone pairs don't count.
Right. Now, if the heteroatom is only singly bonded within the ring, like the oxygen in furan or the other nitrogen in imidazole, the one with the H on it, then it can usually contribute 1 lone pair, 2 electrons, to the pi system if doing so helps achieve aromaticity, i.e. gets it to a 4n plus 2 number.
So furan's oxygen is single bonded, contributes a pair, gets to 6, aromatic.
Yep. Imidazole has 1 double bonded N, lone pair doesn't count, and 1 single bonded N, lone pair does count, plus the 4 electrons from the CC and CN double bonds. Total equals 6 pi electrons, aromatic.
That shortcut seems really helpful.
Yeah.
Okay, so we can identify them. How does this stability stuff affect other properties, like acidity or basicity?
Great question. This is a classic application. Aromaticity is all about stability, right? So when you're comparing acidities, you always look at the stability of the thing that's left after the proton leaves the conjugate base.
More stable conjugate base means stronger acid.
Exactly. So compare cyclopentadiene and cyclobutadiene again, which is more acidic.
Okay, if cyclopentadiene loses a proton, it forms the cyclopentadienyl anion. 5-membered ring, 2 double bonds, and a lone pair on the negative carbon. That's 6 pi-electrons.
Right. And it's a ring, flat, continuous p orbitals. So the anion is aromatic.
Ah. So losing the proton makes it super stable.
Very stable. Now, what about cycloheptatrine? If it loses a proton, you get the anion. 7 carbons, 3 double bonds, 1 lone pair. That's 8 pi-electrons.
8 electrons. That's furan. Anti-aromatic is flat, or maybe just non-aromatic. Either way, not stabilized like the cyclobutadiene anion.
Precisely. Since deprotonating cyclobutadiene leads to a highly stable aromatic anion, cyclobutadiene is way, way more acidic than cycloheptatrine. Its pico is around 16, which is incredibly acidic for a hydrocarbon.
That makes perfect sense. Okay, flip side. Basicity. How does aromaticity affect how well something accepts a proton, like those 2 nitrogens in imidazole?
Similar logic, but now we look at the stability of the conjugate acid the thing formed after the proton is added. Imidazole has 2 nitrogens. One is like pyridine, double bonded. Its lone pair points outwards. The other is like pyrrole, single bonded, NH. Its lone pair is part of the aromatic 6 pi-electron system.
Okay. Which one grabs a proton more easily?
Well, think about what happens. If the pyrrole-like nitrogen, the NH, gets protonated, its lone pair is now used to bond to the new H+ car.
So those electrons are no longer part of the pi system.
Exactly. You've just destroyed the aromaticity of the ring to add that proton. The resulting conjugate acid is much less stable.
Bad move.
Right.
What about the other nitrogen, the pyridine-like one?
Its lone pair is in an sp2 orbital sticking out, outside the pi system. If it accepts a proton, the 6 pi-electron aromatic system is completely untouched.
Ah. So protonating that nitrogen doesn't mess with the aromatic stability.
Right. So the conjugate acid formed by protonating the pyridine-like nitrogen is much more stable. Therefore, that nitrogen is much more basic.
The general rule then is, lone pairs not involved in the aromatic pi system are more basic.
That's the key takeaway for basicity in aromatic heterocycles.
Awesome. Okay, one last big topic.
Yeah.
Naming these things. Nomenclature.
Ah, yes, the fun part. For simple cases where you just have one group on a benzene ring, you name the group and add benzene, like ethyl benzene.
Easy enough. What if the chain attached is really long?
Good point. If the alkyl chain attached has more carbons than the ring itself, which is 6 for benzene, then the chain becomes the parent name. And the benzene ring is treated as a substituent. We call it a phenyl group, often abbreviated.
Phenyl group. Got it. So like 2-phenylheptane.
Exactly. And the general term for any aromatic ring used as a substituent is an aryl group. Phenyl is a specific type of aryl group.
Okay. And there's that other one people mix up. Benzyl.
Yes. Crucial distinction. A phenyl group is just the C6H5 ring attached directly. A benzyl group is C6H5CH2. It's the benzene ring plus a CH2 linker.
Phenyl is just the ring, benzyl's ring, CH2. Don't mix them up.
Please don't. It causes endless confusion if you do.
And then they're the common names.
Oh, the common names. Yeah. You just kind of have to learn them for many simple substituted benzenes. Methylbenzene is almost always called toluene. Hydroxybenzene is phenol. Aminobenzene is aniline. Dimethylbenzenes are xylenes.
You really got to know those for exams and stuff, right?
Absolutely. They're used so frequently. And beyond benzene, there are common names for other aromatic systems you'll see a lot. Furan, thiophene, pyrrole, pyridine, indole, naphthalene, anthracene. The list goes on.
It's a whole world. Well, what a fantastic deep dive this has been. We've gone from Kekule's snake dream all the way to MO theory and why these rings are just like pillars of stability.
Yeah, we unpacked Hückel's rule, gone through the 4 key conditions for aromaticity, and seen how it affects everything from stability to acidity and basicity. The real core idea is that unique stability from having that perfectly filled set of delocalized pi-electrons and those low-energy bonding orbitals.
Definitely.
Yeah.
So hopefully the next time you see one of these rings, you can quickly figure out its character, aromatic, anti-aromatic, or just non-aromatic, and appreciate, the electron dance that makes it special.
It does make you wonder, doesn't it, given how stable and common they are, especially in biology. How different would life on Earth be if aromatic compounds didn't have this unique stability? Just something to think about.
That's a great thought to end on. We really hope this deep dive gave you a useful shortcut and a solid understanding of aromatic compounds. Thanks so much for joining us.
Yeah, thanks for tuning into our deep dive today.
Until next time, keep that curiosity alive.